Well, hi, everybody. In today's video, I would like to give you an introduction to combinatorics. This is something that we all use in our day-to-day lives. Throughout time, we spend time solving problems that involve counting things and looking at different arrangements of objects. And in fact, if I could give you a single definition for what combinatorics is about, I would refer to it as the study of arrangements of objects. Let's write that down. As a definition, combinatorics is the study of arrangements of objects. These objects and these arrangements can take on many different forms. And that's why combinatorics is really everywhere in our society, right? Have you ever tried to solve a Sudoku puzzle? Have you ever tried to tour a bunch of sites within a new city in a manner that is most efficient with respect to traveling the streets of that city? Have you ever tried to win at blackjack at the casino? Have you ever tried to count how many ways to take a group of people and divide them into groups? These are all problems about combinatorics. It's about studying arrangements of objects. Sometimes the arrangements themselves are of interest, the actual arrangements. Other times we just want to know how many arrangements are there. We would just like to count them without necessarily studying each one of the arrangements in depth. These are some of the ideas that come to the surface when we're studying combinatorics. So again, let me write down a few examples of some problems that are related to combinatorics. So for example, we could ask how many 5-card poker hands contain 4 of a kind. I'm talking here about a standard deck of cards. There's 52 cards in a standard deck, 13 spades, 13 clubs, 13 diamonds, and 13 hearts. And they range between the ace all the way up to 2, 3, 4, 5, 6, 7, 8, 9, 10, and jack, king, and queen. 13 of each kind, 13 different kinds. But if I have all 4 of a particular kind in a hand of 5 cards, that's called 4 of a kind. And we can ask how many of those there are. Again, related to card games, perhaps sitting at a casino table playing a game with cards. Another example would be how many ways can 30 people be put into 10 groups of 3. Again, this is just a very specific example. There would be many other variations on this problem, of course, but this is the sort of thing that could come up in a real world situation. Putting people into groups certainly makes sense. How can a highway system be developed with as few crossings as possible? In other words, we may have a bunch of roads that need to cross each other. And every time that happens, perhaps we need to build a bridge. Bridges are expensive. They take time. And we would like to minimize the number of bridges that are required in order to develop a system of roads on some highway plan. So that would be a place where graph theory actually comes into play, and graph theory is a branch of combinatorics. okay? Another one that's kind of on the realm of graph theory that I could list up here would be what I mentioned to you earlier. What's the most efficient way either the cheapest or the shortest, to visit several tourist sites that are connected by streets in a town. In other words, is there some sort of a process that we can follow that will help us to efficiently visit a bunch of places, wasting as little time or money or other resources as possible? This is another example of a combinatorics problem. So we see that combinatorics involves counting, and it involves graph theory, and it can involve a number of other things as well. The applications of combinatorics are absolutely everywhere. Specifically, any other societal topic where we need to count things, whether it's in biology, whether it's in business, whether it's in kinesiology, right? These different societal topics can all be looked at through the lens of combinatorics to solve a number of their problems. Let me give you a list of, these are just some examples. I guess maybe one more thing in this list, and then I'll move to another list. But Sudoku puzzles, a lot of combinatorics is about games, actually. And those games, while they may just sound like it's for entertainment purposes, a lot of times the reasoning and the thinking that goes into excelling at a particular game involves critical thinking skills that are quite applicable and quite important for solving serious real-world problems. So just one example of that probably everybody is somewhat experienced with by now is the idea of solving a Sudoku puzzle. That's also got a lot of combinatorics in it. It's a very discrete topic. When I say discrete, what I mean is that we're working with whole numbers, right? 1, 2, 3, 4. This is, after all, the way that we count, right? We don't count in decimals. We don't count in fractions, irrational numbers, or anything else. We count with positive whole numbers, integers, 1, 2, 3, 4, and so on. When we're counting how many ways there are to do things, right, we are always going to expect that answer to be a whole number. And sometimes that can be extremely valuable information in terms of how to solve the problem that we're looking at. The fact that the answer has to be a whole number. It can't be some fractional thing. Let me take a moment over here. I'm going to make a list of some of the topics that are often covered when somebody is studying combinatorics, and that in this course, we're going to spend a fair bit of time looking at. So here's a list of some topics that are related to the examples that I just gave you on the previous board. These are topics that come up a lot in combinatorics. One is the idea of the pigeonhole principle. This is more of an idea that is used to prove certain things about a pattern of a process that is going on. So, that perhaps we have a certain number of pigeonholes and we have a certain number of pigeons, and we want to put those pigeons into those holes. There's certain rules depending on the relationship between how many pigeonholes we have and how many pigeons we have, that we can say things about how those pigeons will be arranged in those pigeonholes. So the pigeonhole principle is certainly an important part of combinatorics. But there's really nothing that would come more to the surface when we're talking about combinatorics than the idea of counting strategies. How can we count how many arrangements of objects that we have? So there are a number of things that we can do in the realm of counting that I'm going to list here. The first thing is we have some basic principles about repetition of objects And what I mean by that is when we are counting things, it might be that objects can be repeated. And it might be that they cannot be repeated. So this is allowed or not allowed. And it makes a big difference in our counting strategy whether repetition is allowed or not. For example, if I'm writing out license plates to cars, the characters that are on that license plate generally can be repeated. You can have the same character on a license plate multiple times. On the other hand, a very different situation might be officers of a club where you have a president, a vice president, a treasurer, and a secretary, and none of those four positions can be occupied by the same person. In other words, no person can be repeated in more than one officer role. In that case, repetition would not be allowed. And the answer to how many ways there are to count arrangements of either license plates or officers of a club is going to be different because of the issue of allowing repetition or not. The other aspect of this that is important is not only do we care about whether objects can be repeated, we also care about whether order matters, the order of the objects, whether that matters or not. Yes or no? Does the order of the objects matter? So, for example, if I'm writing down a license plate, the license plate A, B, C, D is not the same as the license plate C, D, B, A. The order in which the characters are listed in that license plate affects the license plate. And even if the same characters are being used in two different license plates, if they're not in the same order, they would be considered different license plates. On the other hand, if I'm just trying to put 30 people into 10 groups of 3, in those groups of 3, we have 3 individuals that are not really in a particular order, right? We just have Nancy, Freddie, and Gabriel, right? And doesn't matter, there is no first, second, or third among those 3 people. Nancy, Freddie, and Gabriel, they can be rearranged and listed in a different order. It's still the same group. It doesn't count as a different group. So sometimes the order does not matter. It's a yes or a no. So what you can see here is that there are going to be 4 different scenarios, right? Order matters and repetition is allowed. Order matters, repetition is not allowed. Order does not matter and repetition is allowed. And order does not matter and repetition is not allowed. We can mix and match these yes and no questions about allowing repetition and about whether order matters. And all 4 of those different types of counting problems will have a slightly different approach. And we'll get slightly different formulas, slightly different answers for how many arrangements are possible. So we're going to spend some time studying those 4 different types of counting strategies. Sometimes the hardest part of a problem is just deciding which strategy are we using for a particular problem. In other words, it might be hard to even decide, does the order really matter here? And is repetition really allowed here? It involves sometimes some careful thinking and can be sometimes tricky and it can lead to confusion sometimes if we haven't practiced this enough. So this is something that definitely takes practice. We are also going to study a very well-known principle called the inclusion-exclusion principle. This is a way of counting, sort of counting in the context where there might be multiple ways for an arrangement to be counted. And we would like to count each arrangement only one time. We don't want to overcount the arrangement. You can imagine that there's a number of little tricks to counting. This is one of them. The inclusion-exclusion principle is a very valuable tool for helping us count arrangements of objects. Even on a more fundamental level, we could count arrangements of objects by, instead of counting what we wanted to count, we could actually count what we don't want to count and subtract from some sort of a universal total, right? So almost by what I would call a complement idea, counting what you actually don't want to count and subtracting from some universal total. We'll talk about that, right? Sometimes it will be easier to count something by double counting it, counting all of the arrangements twice, or maybe 3 times, or k times. It's somehow that by doing that, the counting is more natural, and it's easier to compute k times the number of arrangements than it was to just count the number of arrangements in the first place. Sounds a little bizarre, but these are some of the tricks that we like to use that are kind of along the lines of this inclusion-exclusion principle. Another popular trick for counting things is to use what are called recurrence relations. Recurrence relations basically allow us to count arrangements of objects by counting a smaller version of that same problem. So in other words, maybe with fewer objects. It's almost like an induction approach, where if we want to count how many ways to arrange, say, n people, subject to certain constraints, maybe we first would figure out how many ways are there to arrange n-1 people, and then inductively build up how many ways there are to arrange n people. We're going to use recurrence relations to do something like that. This is, again, another very standard topic in combinatorics. Finally, one of the strategies that I'm looking forward to sharing in this course is to actually use group theory and permutations as a mechanism for counting things. Let's say we have necklaces that have colored beads. And of course, if I take a necklace and I pick it up and twirl it around or whatever, it's not really changing the necklace. It's the same necklace. We're just picking it up and rotating it or flipping it or something like that. Yeah. I don't want to count rotations or flips of a necklace as giving me a different necklace. That's still just one necklace. So we're going to use certain ideas from abstract algebra to help us make sure that we don't overcount the number of objects in the cases where the objects are obtained through rotations and reflections, various symmetries that we might perform. So this is a little bit more advanced topic in the realm of counting strategies, but it is definitely something that we want to take a look at. What other things come under the umbrella of the topics of combinatorics? Well, another idea is something called combinatorial identities. These are formulas. These are formulas that involve whole numbers. These are discrete expressions that involve standard expressions from combinatorics, combinations, permutations, factorials, things of that nature. And sometimes we can take relationships between these different combinatorial symbols and discover that those relationships can be proven by something called a combinatorial proof. Combinatorial proofs are a very important and powerful tool in this field. Essentially, what you're going to do is you're going to prove that two combinatorial expressions are equal to each other. In other words, that they form an identity. They are equal to each other, and you can prove that by counting something. In other words, forget about just plugging in numbers, forget about actually calculating factorials or combinations or permutations numerically. Instead, find some process that you can view from two different perspectives. And because it's the same process viewed two different ways, the number of arrangements that you are looking at is the same. But from one viewpoint, the expression, the combinatorial expression that you have looks very different than when you count that same process from a different perspective with a very different expression. So this is a really cool thing, and I'm looking forward to talking about combinatorial identities. I mentioned earlier that combinatorics is also very closely related to graph theory, and we are going to spend some time in this class talking about graph theory. I mentioned the idea of going around to different tourist sites in a city as efficiently as possible, or building a network of highways that have as few crossings, as few bridges as possible. These are ideas from graph theory. And when we have a graph, we can do things like colorings of the graph. I've just mentioned crossings of the graph. We can study sort of optimal ways to color a graph or to create crossings. We can study paths, cycles, trails, etc. Different ways of sort of moving along the edges of a graph. At its fundamental heart, a graph is basically a collection of vertices and edges. There's some details and there's some variations on what a graph is that we have to very carefully spell out and define. But just for this introduction, think of a graph as a set of vertices with edges, and you simply walk along the edges of that graph, forming a path. And you may have a variety of objectives. Maybe your objective is to visit every single vertex while taking that walk. Or maybe your objective is to visit every single edge, to walk along every single edge while you're perusing through the graph. And we can find out that some graphs we can't visit every vertex without repeating some edges of the graph. Or maybe it's not possible to visit every edge of the graph and end up back where we started again. Things like this are interesting problems about graphs. Again, these are discrete objects where we can think of them as combinatorial in nature. These are just a couple of quick ideas, a few quick ideas about the types of examples that you can have when you're talking about combinatorics, as well as sort of an overview of some of the topics that are involved in combinatorics. Certainly not a complete list here, but it gives you an idea, and certainly in any first course on combinatorics, we would want to talk about as many of these topics over here as we possibly can. I'm looking forward to it. I hope that you are too. These are fun problems. For the most part, these are problems that are fairly easy to understand. We don't have to have a huge background in order to ask these questions. How many 4-of-a-kind poker hands are there? Or how many ways to put 30 people into 10 groups of 3? These are not questions that require deep understanding of mathematics to ask, but they're the kind of questions that anybody could ask. And as I said earlier, combinatorics is really ubiquitous. It is everywhere in our society and in our day-to-day living. So it's something worth spending some time exploring, and I'm looking forward to doing it. Thank you so much for watching this introductory video about combinatorics. I welcome any questions, and I look forward to seeing you all again very soon in the next video. Bye for now.